We're from AAT, Applied Automation Technologies, and today we're going to talk about CappsNC, our on-machine metrology software. As Eric said, this is a four-part webinar series. The first webinar is the introduction of AAT and the CappsNC software in general, and basic part programming. So after we get through all of the beginning part, when we talk about the software and what it can do and how it can help you, we're going to run through a quick demo of the software. So I'll load a basic CAD model. It's everybody's favorite AAT demo block. We'll create a general probing cycle, simulate it, and then post GCode for a FANUC 31i controller. And then from there, we will build on that to talk about different options that are available to us. Like webinar 2, for example, will be adaptive pre-process setup and work offset, so how we can modify a work offset using a probing cycle. Webinar 3 will be adaptive machining, so we're going to incorporate a probing cycle into a cutting cycle. It's a process that we call measure, cut, measure. And then webinar 4 will build on this first webinar using this same program, and we'll talk about reporting and the gd&t functionality that's available to us in the CAPS software. So moving on. So a little bit about us. If you're not familiar with us, Applied Automation Technologies is a software development company founded in 1987. Back in 1987, Applied Automation Technologies was credited with creating the first CAD-based inspection software for coordinate measuring machines. Then from that time until current time, we've worked on updating, correcting, and implementing new processes to be used in that space. In 1992, the software was first applied to a CNC machine. It was used on a water jet machine to help a customer to drill holes in wing spars on a very large part. They were having trouble with getting these hole locations in the right place, so the software was adapted to work on the water jet machine to create small localized alignments so the holes could be put in much more accurately. So now fast forward a couple of decades, in 2007, the CappsNC product that we have today that we're going to be talking about is really when that software was born. It was adapted for a customer that asked us if we could do on-machine probing. And at that time, it seemed the market was pretty prime for us to develop a solution like this. So that's kind of how that went. So our software solutions connect metrology data to the manufacturing environment through on-machine measurement. Okay, so we have some, just about everybody nowadays has a probe inside of their CNC machine. So we allow that probe to be utilized to inspect parts, but more from a metrology standpoint, not just a probing standpoint. So we like to say that we are a probing software, but also a metrology software at our core. Once you get that information from the part, we have a real-time connection to the machine, which offers closed-loop automatic feedback for adaptive systems. In other words, you can probe features on the part in real time while the operation is running. You can process that information, send it back to the controller, and make real-time decisions. Some of the decisions that we can make are to adjust tool offsets, to adjust work offsets, and also to make real-time decisions during the cutting cycle. So if you drill a key feature or machine a key feature, you can probe that feature in cycle and use the results of that measurement to make real-time decisions to determine whether or not the part should be continued to be measured, or maybe some process has to be stopped and modified or something like that. But all this can be done automatically through the closed-loop adaptive feedback. And of course, we apply in smart manufacturing, Industry 4.0, or some of the terms that are being used today to talk about this type of application. So on-machine measurement, metrology software for NC machines. So what is CappsNC really? So CappsNC is a metrology software, and on the NC side, it's based around an offline simulation and or programming environment. So we like to say it's a CAM programming environment. And one of the ways that the software stands out is in terms of other probing softwares is that we have path optimization and simulation, as well as flexible path geometry. So, for example, if you're probing a circle and you need to measure 85 points in that circle, it's pretty easy and straightforward to generate that path dynamically on the screen automatically just by clicking on the CAD model. Some probing solutions, you're locked into a certain number of points, or you're locked into certain geometric characteristics that you can measure, whereas with the CappsNC software, you have all of the options that you would find in a typical metrology software. So we offer features such as toruses, such as ellipses, cones, some features that might not be available to you in other softwares. Okay. We also offer the availability to apply a complex alignment to a work offset. So some of the options that we offer a 3 tooling ball alignment, which is good if you're measuring a part in a fixture. We also offer a 3D best fit. So if you have a complex shape or some non-prismatic part that you want to align with our software, we have the capability to not only probe the information on the machine, but also calculate up to a 6 degree of freedom alignment for that part. And if the controller is capable, we can apply all 6 degree of freedom of that alignment back to the work offset, update the work offset, and then machine and allow you to machine in that work offset. Because we are a metrology software, we offer CMM style reports with functionality and compliance to the ASME Y14.5 2009 gd&t spec. So we have capabilities in the software, and that will all be shown in webinar number 4. Okay. Our software is, because it's a metrology software, our software is based off of DMIS code. Okay. If you're not familiar, DMIS is to CMMs what GCode is to CNC machines. And once again, because we have worked in that environment for over 30 years, we stayed in that environment. However, we have created our own GCode posts for most major CNC machine controllers. So you generate the program inside of CAPS. The program can be viewed either as a tree, an object-based tree, or as DMIS code. Once you're completed with your program and you're happy with it and the simulation looks as you expect, we then have a post built into the software. You then post the DMIS code through the GCode post to generate the GCode program. Okay. Now the style of GCode that we generate is a macro-based GCode program. So when you look at, and we'll look at this towards the end of this discussion, when you look at the GCode, it's a bunch of macro calls. So we don't do direct measurement inside of the GCode. We have macros that we install in the system that handle movement of the machine either around in a safe move situation or as a probing situation. So we have macros to handle all the different types of movements that we would need from the DMIS program. Okay. We offer real-time connection to the machine controller. So this is all based off of the standard Ethernet communication protocol offered by the controller manufacturer. So if you're looking at, Fanuc, for example, it's Focus, Siemens is OPC, and so on and so on. All the controllers have their own direct Ethernet communication. This real-time connection allows us the functionality of being able to feedback directly into the system. Right? So if we want to write to macro variables, or when we want to do a tool offset, or we want to do a work offset or something like that, this real-time connection is what makes that possible. And then finally, because of the real-time connection to the machine, we can easily incorporate our measurement cycles into cutting programs with feedback to macro variables. So let's say that you have a system in place, you have a cutting cycle that you want to adapt or implement probing cycles in. In that case, you would just develop the probing cycle. The probing cycle would have to manage itself, or you would have to manage, a tool change or anything like that leading into that probing cycle. But in that case, the cutting cycle is the master. So the cutting cycle is what calls the probing cycle. Now, we do have functionality built into the CAPS software for adapting this in the opposite way. So in other words, the probing cycle could be the master, and we could call cutting cycles. And it all depends on how you develop and manage your GCode files. But the point there is that we can, cut a portion of the part, probe it, make some decisions based off the results, and then feed that information back into the control and have the system basically make decisions for itself. Okay, so the software that we have, all the software that we're talking about here, kind of breaks down into a couple of different blocks here that we show. So on the left, we have our CappsNC simulation. The CappsNC program sent directly to the shop floor, machine computer or control panel via DNC or other transfer protocol. So you could have your CAM environment, we call it a programming station, live in engineering, for example. That's all the program development can be done there. Then you would send it out to the machine. You would have a PC next to the machine. There we have real-time execution. So there you would handle your sensor calibration from there. The programming, as it's probing around the part, it would be sending information back to that system there. We'd then be generating reports. We could do live feedback, anything at that point. Okay. The CappsNC pre-process approach allows users to set specific work offset and tool offsets before the machining process, so you could load the part in, probe some key features on it, make some decisions based on that, and have all that happen right at the machine. Quality reports. The software can be used as a CMM at that point. Obviously, there are considerations that need to be taken into, or there's things that need to be taken into consideration to ensure that the machine is capable of probing and acting as a CMM. And we can talk. If anybody has any questions about that or wants more information, we can send you information related to how we manage all of the typical questions or items that people ask about when probing on a machine. And then finally, all the metrology data can be logged on the machine for further SPC control and analysis. And we also offer different tools in the software to allow us to dump information directly into certain SPC softwares. So this is kind of a nutshell of CAPS and how it works. Okay, so I'll go to the next slide. So how is CAPS used? So everything we're talking about here is, okay, yeah, we're going to probe on the machine, we're going to perform this metrology data on the machine, but what can it be used for? I don't want to turn my machine into a CMM. Well, that's okay. If you don't want to, you don't have to. You can if it's something that interests you. So we like to break it down into 3 different sections. So you can use CappsNC pre-production, you can use in production, and you can use it post-production. So if you use it pre-production, you can use it for incoming inspection. So if you have a casting or some partially machined part that's coming in for the operation that you happen to be working on, you can probe some features and do incoming inspection on the part before you actually start to machine it. You can set a work offset. So if you don't know where the part is at all, you can generate a cycle that will probe the feature, probe features on the part and set a work offset from scratch. And you can also refine an existing work offset. So you would say, okay, I'm going to activate G508, for example. I'm going to probe some features and I'm going to update the location and orientation of G508. And then I'm going to go on and machine my part in that corrected work offset. In production, you can use it to update tool offsets, you can use it to update work offsets, and you can use it for in-process feature validation with feedback to macro variables. So imagine you're doing an interpolated cut on a hole, so you're drilling a hole, and as that tool starts to wear, that tool is going to get smaller, and your size of your hole is going to change along with that tool size. Well, if we jumped in there and probed the hole after we were done, we could kind of see a trend of how the hole size is getting smaller and smaller based on that, and use some characteristics to determine, okay, when it reaches this certain point, now we're going to update the tool offset. And now next time we use that tool to drill that hole, we're now going to drill a hole is closer to nominal than it was previously. And you can also set limits in there to say if we get to a certain point, then either load a sister tool or change the tool, warn the operator, anything like that. Update work offset. Imagine that you have a localized hole, like a hole pattern, for example. So you might have like a 3 or 4 hole pattern going around a center hole. And it's extremely important. The true position, let's say, is very tight of those holes in the hole pattern to the center hole. Well, you could machine the center hole and then probe the center hole, update the work offset based on the deviation of that center hole. And now when you drill the holes in the pattern, they're going to be a lot closer to the center hole than they would be if you didn't do that. Okay, so let's say you're maintaining, let's say, a true position tolerance of 5 thou or something like that, something that's really, really close. And then finally, in-process feature validation with feedback to macro variables. So one of the things that we do during our measure cut measure process is we set a bit for the cutting cycle to read. So let's say the cutting cycle does its thing. It calls the probing cycle. The probing cycle probes the feature and determines if the feature is, let's say, out of tolerance. Well, it could say, okay, I'm going to set macro variable pound 53, for example, to a 1. And then when it jumps back into the cutting cycle would read pound 53 and say, oh, it's equal to 1. That means I got a problem. I should stop, or I should do whatever I'm going to do based on that macro variable being set to 1. And then finally, we have post-production. So post-production can be used for first article inspection. So let's say you're setting up a part on a machine and you want to probe that part. Now, typically, how does it work? So the part comes off the machine and goes to inspection, and you wait. You wait until inspection can get to it and give you your results and say, yes, your setup is good, or no, your setup's bad. Well, imagine if you could probe key features on the part in the machine and probe key features on the part in the machine and then make a determination whether or not you should continue with manufacturing your parts. Once again, we're not looking at this as a way to eliminate first article inspection from the inspection room. What we're doing is we're allowing the operators to run at less risk, right? Because typically what happens is if, let's say, your turnaround time for first article inspection is 2 days. Well, you can't wait 2 days to make production. So what do? You run at risk. Well, imagine if you could run at less risk and have more confidence in the parts in your setup so that you know that the parts that you're making are going to be good. And then in 2 days, when you get that result back from the inspection department that say, yeah, this part's good, you're say, cool, I already made 50 of them or 60 of them, whatever it may be. And then also another way it can be used post-production is visual reporting at the machine. So we can set the system up in such a way that the operator just looks at a screen. Green is good, red and or blue is bad, and they make that determination. So they're really not even looking at numbers. They're just saying, okay, yeah, this part's good or bad. So you can think of it like a go, no go type of environment. And then, of course, we have full part inspection. So you can take as much cycle time, and you can probe as much as you need on your part right in the machine if that's something that you choose to do. Okay, so those are the ways that CappsNC is used in the 3 different, let's call it, environments of manufacturing. Okay, so how does all this fit into our ecosystem? Well, the CappsNC ecosystem, it's kind of like an a la carte software, right? So you have the CappsNC software, and we have basically 3 versions of it. We have Advanced, which does everything. We have Programming, which gives you the CAM programming environment, and then you have the Execution module, which is what connects to the machine and gets the data. So depending on how you want the software to be licensed for your application, we offer different options for that. In terms of other tools available to us, if you don't want work offset, you don't have to have work offset. If you don't want tool offset, you don't have to have tool offset. So all of these a la carte functions allow you to kind of build a software that you need with the functionality that you need. Now, if you do down the road determine, you know what, I actually do want tool offset, right? You could purchase that option and we send you new code and now you have that option. So it's not like you need a complete software change or anything like that. Some of the other options that we offer on top of that is we have NC Fit, we have a laser interface, and we offer a software called Data View Feedback. So just 30,000 foot view. NC Fit is an application that will allow you to modify your GCode, your cutting paths based off of measurements. So if you have a flexible part, some non-rigid part that is going to differ from part setup to part setup, you can incorporate that part flexibility into the G-code and have the system process that in that way. Laser interface would take place of a touch probe. So you can incorporate a blue light laser scanner into your machine, and rather than probing points, you can actually scan points. Okay. So that's about it for that. Okay, so just real quick, I'm talking a little long here, so we're at 2:20. So let's just kind of go through this real quick. This is what we're going to do. We're going to use our CAM environment to create a geometric part inspection. Then we're going to create the G-code for a FANUC. We're going to talk about how you upload it to the machine, and then we'll run a video that shows the program running on the machine. So without further ado, I'm going to jump over to Capps real quick here. We're going to skip the questions and answers for right now and save that till the end. So I'll bring up Capps. So here is my Capps environment. And we'll go from here. Okay, so this is the new, what we're calling our V8 or new version software. So let's talk a little bit about what we have here. So this quick menu here is how we get into the software. So we're going to make a new program at this point. So I'm going to click on New. When we make a new program, we would enter a name up here at the top. Let's just call it Webinar 1. Here I can choose a location. I can also pick a CAD model. I can choose a report template, and I can pick a probe. So for right now, because we're not talking about reporting or anything, we're not going to do anything with the report template or the details down here. So I'll just pick my probe here. Okay, we'll load a CAD in a second, and I'll go ahead and hit create. When I hit create, it's going to open up the software, get me into this environment. Okay, so now you can see we have a report window down at the bottom. We have our code window here on the side, and here's our programming environment. So let's go ahead and load a CAD model real quick. So I'm going to load in a step model. Here we go. Okay, now we're going to check a couple of things before we get started. First thing I'm going to do is I'm going to go here to the Measure toolbar, and I'm going to make sure that my settings, probe toolbar, I'm going to pick settings and make sure that my settings are good. So I have my approach, my search, my surface clearance, my position speed. So right now my approach is 1, my surface clearance is 10, search is 10, sampling approach and retract is 1, and position speed is 2,000 millimeters per minute. So pretty quick. Okay. So I like all these. If I wanted to change one, for example, let's say I want to change surface clearance to 5, I can just do that and click OK. When I do that, it's going to add to the program the parameters that I just set. The next thing I want to do is I want to take a look at my collision avoidance here. So while we're programming this, we want to make sure that the probe is not going to collide with the CAD part. So I have different options. I have none, which is off, plane, which is an absolute plane that doesn't use CAD. I have auto plane, which uses CAD but drives to an absolute plane. And then I have auto distance. Auto distance is my favorite. This is going to look at where the probe is sitting, where you want it to go, and it's going to make decisions based on that. Right now, it's going to move in 10 millimeter increments. I'm going to change that and make it 5. Okay, so now we've got our probe settings set up and all that. So now I'm going to go to my measurement toolbar. Sorry, my little WebEx toolbar here is kind of in front of everything. So now I'm going to go ahead and start doing some measurement. So the first thing we're going to do is enter a position point, which will be the start point for my program. So we're going to move to a position of 0, 0, 50. You can see here that when I do that, the path shows up on the screen. Okay, so I can close that. The next thing that I want to do is I'm going to measure my key features or my base features for my alignment, and then we'll measure some features on the part. So starting with the plane. Okay, plane is one of those features that's a little bit different. Here, I can use the cursor to teach each individual point of the plane that I want to measure. Once that path is good and I'm happy with it, I can animate it if I'd like to, see what the system's going to do before it generates any code. Okay, and then if I'm happy, I can hit measure. Cool, so now we have a plane. The next feature type that we're going to pick is we're going to pick a line on the back and a line on the edge here to recreate this alignment in Caps. So let's whip around here a little bit. Let's go to line, click on the CAD. There's our measurement path there. So that looks good to me. Now at this point, I could increase the number of points if I want. However, I can't go less than 2 in this case. So that looks good to me, so I'm going to hit measure. Okay. The next line that we're going to measure is going to be on this edge here, so I'll just click here on the CAD. So the software invokes the collision avoidance, brings it up around the part, but I notice here that the line might not be the direction that I like. That's okay. I could just inverse the vector direction, and the software will modify the path accordingly. Okay. All right, so now we've got a plane. Let's do this. A plane and 2 lines. Okay, so now we're going to go ahead and measure some geometry on this part. First thing we're going to do is measure a cylinder. So I'm going to click on the cylinder option here, and I'm just going to click right on the CAD. Okay. Well, when I do that, okay, I can see my path drawn on the screen here. The probe's going to come up, over, and it's going to probe like this. Now, one thing I want you to notice real quickly is that the path is bounded by the cylinder itself. So we're going to reduce that. So the first thing we can do here is go to offset and bring that path in a little bit. Okay. I could also move the location, which would move the whole path up and down. Okay. The next thing is I'm going to look at how many points I have. So right now I have number of points set to 9. So the software automatically gives me 3 levels of 3. Okay. When we measure the next feature that is, we're going to measure a cone eventually. So there we'll talk about this levels option. So at this point, everything looks okay to me. I'm going to go ahead and hit measure. Cool. So there's my measure. Next, we want to do some circles and things on the top of the part here. So we'll go to circle. Click right here on the CAD. The software is going to generate the path for me. Now, here I can adjust the points. Let's say I want 10 points inside of that hole, and you can see the software just dynamically changes the path based on what I enter. Okay. So location is the depth. So right now we're going to go 2 millimeters below the surface to perform that measurement. That looks good to me. Let's animate it. That's a little fast. Let's turn the speed down. Measure. Perfect. Okay. Now, probe's going to stay in the hole. I click on the next one. It's going to make the path for me. Now, let's say this one I only want 6 points. So I'll drop that down to 6. Measure. Okay. Now, we're going to measure this cone. So inside of this cone here, we're going to click on the CAD. The software is going to generate the path for me. Okay. But here I'm going to check this levels box. So in this case now, it's telling me I'm going to get 3 points per level with 2 levels. So let's up this to 4 points, and let's up the number of levels to 3. So now we're getting 12 points. The next thing I want to look at is my path. So let's make our offset a little bit lower here. Kind of stretch that out a little bit, cover a little bit more of the cone. And let's set the location at 0. Cool. All right, so at this point, we're good to go. We can hit measure. So there's our cone. Let's bang out a couple more circles. So let's go here. Good. Looks good to me. Okay, and then last but not least, let's grab this circle here. And that's going to do it for the geometric features that we want to measure. Okay. Next, we're going to go down here. We're going to measure some points on this front edge here, and then we're going to do some points on this side edge here. So the front edge here, we're going to just do point by point. So this is a really good tool. If you don't have a lot of points on the surface that you want to measure, you can just click right on the CAD. The software will generate a path, and then we'll invoke what I like to call the lazy man's way of doing this. Click, measure, instead of coming all the way down here to the measure button. So click, right-click, measure, click, right-click, measure, and I can go all around the surface just like that and measure the points that I want. Okay. Now, like I said, this is a great tool for using it, for measuring just a couple of points here and there. But let's say that I wanted to interrogate a surface a little bit more. I wanted a little bit more points, and maybe I wanted to define a little bit cleaner where the points are located on the surface. So if I close that and I switch the software now to what we call nominals mode, I'm going to select the surface that I want to measure. In this case, this little side surface here. Okay. And we're going to do what we call cross-section or section cutting. Go to surfaces, bring up section cuts. Now, in this case, I have the option to do just a single section. So if I just click here, I'll get one cross-section right there. That cross-section is along the x-axis, meaning every point in that cross-section has the same x-axis coordinate. But I don't want to do that. I'm going to choose Y. So now I can click right here, and there's my single section. Okay, but I don't want to do that. I want multiple sections. So choose the multiple sections option, define my first boundary, define my last boundary. Okay, now I've got, you can see here, I've got 4 cross sections. So the cross sections are either based off of the increment number set here. So these are approximately 10 millimeters apart. I prefer to use the number of sections option, which says, you know what, just give me 3. All right. The next thing I'm going to do is I'm going to say fixed number of points. So how many points do I want in each of these cross sections? I have 3 options. I can either fix the increment between points, so take a point every 5 millimeters. If I know that my surface is changing, I can choose the optimization function, which will say put the spacing at 5 millimeters, but if the direction or the curvature of the surface changes, reduce the spacing between the points to give me a higher density of points on surfaces that have more curve to them. Okay, and then the last one, which is my favorite, is just give me 5 points. And this is going to be 5 points per cross section. All right. The last thing that I want to look at here is avoiding the edge points. So you can see here that these white lines that define the preview here come right to the edge where these two surfaces come together. Well, considering that I have a 2 millimeter probe, might not, 3 millimeter probe, might not be able to hit that surface. So I'll just say avoid edge points, and I'll avoid them by, let's say, 1.8 millimeters and 1.8 millimeters. And now that's going to reduce the stretch here, bring me in from the edges of the surface. So that looks good to me. So let's see what we get. So I'll hit generate, and the software is going to generate 3 cross sections, each with 5 points. And all of the points, as you can see here, are vector normal to the surface, so that when they probe on the actual part, they will probe in that same way. Okay, so other options I have available to me is we could have given these points specific labels if we wanted to. We could have also said, instead of incrementing the points, if we were doing increment spacing between points, we could increment it along the curve or along the axis. So all these tools are available for you to get the best coverage possible through this option. So I'm pretty happy with what I see here. So I'm going to go ahead and just close this. Okay, close this window here. All right, so now we've got 15 points on this surface that we want to measure. So let's talk about what's the easiest way to measure these. Now, I could, if I wanted to, switch back to my Measure CAD, which is my path generation mode, click on point, and use select and pick each point one at a time, one at a time, one at a time, one at a time. Well, I don't like to do that, so we'll use an option that we call path options. So down here in the measurement toolbar, we have this option here called path options. When I click on this, this is going to bring up my toolbar here, or my dialog for what we call nominals grouping. Okay, I will then use the select box option. I have different options. I could do teach, pick the points in any order I want. I could do generate, where I pick the first, pick the last, and the software will go numerically through the points. I can select all. I can eliminate a path once I make a path, or I can use box. So I prefer to use box. So we'll just box this in. You can see here the system generates the movement path for me, starting at the sphere here and moving through the points like that. So there's the path that the system's going to follow. Okay, if I'm happy with what I see, now let's say I wanted to go the other direction, I could simply choose one of these options here to change the order in which the points have been selected. I can pick a point, move it up and down the list. I also have optimization, an optimization function here, which will try and generate the shortest path through all the points. Okay, but we're just going to use the order that the software came up with here. So when I'm good and ready, I can hit the execute button, which is right down here. The software is going to ask me what I want. How do I want to keep my destination data? Do I keep them as points? Do I want to make a curve out of it, or do I want to make a surface out of it? This is all dependent on what you want to do with the data. For now, we're just going to keep it as points. So when I hit OK, the software generates the path and moves its way through all the measurements. Okay, the feature path execution is done. We'll close this. All right, so I am done with my measurement. Okay, so now we're going to bring the probe up. I prefer to move my machine in nice linear fashion, so I'm going to move it up and then bring it back to my end position. So I'm going to go here to position point. I'm going to punch in 50 because that's where I want it to go in the Z, so it will drive straight up. And now I can use these two boxes here, type 0, 0, and move it back here. Now, if I wanted to, at this point, I could use these options down here to move the X or Y incrementally like this. I can also change this value here so that my incremental step is smaller. And the white dot identifies where the probe is going to end up, and the green path shows where it's going to go. So if I don't like a particular position point that I've created, I can just click anywhere where there's no text in this dialog, reset it, and then just punch my numbers in because I know where I want it to go. And there we go. So we are finished. So once again, just to review, we probed a plane. We probed a line across the back, a line along the edge. And then we've probed a cylinder, some holes, a cone, some points on this front face, and then some points on the side face. Okay. So now a good step to do is to simulate our program to make sure that everything looks good. So I'll go back to my main toolbar. I'll choose the run option, which is my run simulate option. And then I can choose to simulate it. When I do this, the system's going to recreate that same measurement path. Let's turn the speed up a little bit. All right. Now, the one thing I forgot to do when we did that is I also have the option here to enable our collision avoidance during simulation so that if we had made a bad move somehow or removed a point or something like that, the software would pick up on that collision and it would warn us, and then we could make corrections and make modifications based on that. So, okay, so at this point we have our program is done. Okay, so now we want to move it out to the machine, but let's just review here real quick what we're looking at. So over here on the right, we have our tree. Okay, so we have all of the movements and all of the features that we've measured here. And if you're old school like me, you can also view this as DMS code. Okay, so at this point, I kind of like to show this. So if we look here, let's just make this window a little bit bigger. So let's look at this first go-to. So the first go-to is to X0, Y0, Z50. And we'll talk about why that's so important in a minute. So we'll put that back. Actually, we'll just rearrange screen. And now we're going to post to NC. So if I click on post to NC, here, because I'm set up for FANUC, I would enter my program number here. My machine start and my machine finish files are shown here. These are nothing more than header and footer files for the post. You can put whatever data inside of this file that you decide that you need, as much or as little data as you decide that you need. Okay, same thing with the finish file, which is our footer. Okay, here we have a couple of things that we're doing. Next, we have how are we going to post our program? So we have two options. The first option is going to be we're going to run it in absolute part offset. In other words, I have a work offset that I've already set up that I'm going to use to probe this part. That work offset is typically going to be set right here in this corner so that when you run the program, everything matches up. Okay, the other option is to run from machine location. This is a great option if you're setting up an initial work offset on a part. So what you can do is you can identify a start move point and then identify that same location relative to the part on the machine to the operator. So they would manually position the machine. They would jog the machine to that spot and start there. And that would allow you to put the part anywhere on the machine that you want and run the same program because the machine would then learn where the machine is sitting before it takes off and apply that to all the movements. Okay. Now, I will say that the majority of our customers use the run in absolute part offset option simply because they don't want to have to worry about, they don't want the operator to have to worry about centering or locating the machine at all before they start. Okay. Now, if this were a head-head type machine, we could create a calibration file that goes along with this that would calibrate all the different head orientations that are used, which we'll talk about that more in a future webinar series. We'll talk about 5-axis probing. So at this point, everything's all set up. Everything's identified. I've got my program execution coordinates identified, so I'm going to go ahead and click OK. So it's going to run through the program again. There we go. One last surface, and there we go. Now, here's our GCode file. So in this case, our program name is going to be 0750. Okay, so we have our start file, which basically goes to this line. So this is the same code that's going to get put at the top of every program. Okay, and then we have, here's the beginning of our movement here. So we have a measure speed identified, we have a position speed identified. So all this is standard FANUC G-code using standard FANUC macro variables. So the thing I wanted to show is it appears that my post is set up for inch, maybe. Looks like it. So my numbers are a little bit different. But if we look at the first move here and try and relate it to this move here, we can see that it's typically a 1-to-1. That's interesting. I don't know where those numbers came from. I'll have to look at that. But you can see here, we have a go-to, so we call macro P801. We have P801 here, which is another clearance move, P800, which is the first PT measure touch here in the code, PT measure, PT measure, PT measure, all line up with the different macro calls here in the plane measurement. Okay, so this program basically would get uploaded to the FANUC controller. We have a communication module that we have to run that connects CAPS to the machine. Once we get that connection established, the operator would just call up the cycle like any other cycle on their machine, hit cycle start, and it would switch to the probe, and then probe the part, and then give us the results, which we don't have yet, which we'll talk about in webinar 4. So that's kind of a nutshell of how to do basic programming inside of CAPS. I hope that was informative for everyone. And that's kind of was the point of this first webinar, was to kind of just give a brief overview, talk about us a little bit as a company, and then also give you a general idea of how to program inside of CAPS. So I'm going to go ahead and ask Eric. Do we have any questions, Eric? Uh-oh, did we lose Eric? I'm going to unmute him. There he is.
Here I am.
All right.
Yeah, thanks, Chris. No questions so far. So
okay. Well, I think at this point, if nobody else has any questions, I think we'll call this our first webinar, and this will be posted probably in the next couple of days. We'll post this online, probably on our YouTube channel, so people can access it to reference back to it. And once again, if any of you guys have any questions, do not hesitate to reach out to us, and we can answer them for you. So I'd like to thank everyone for coming. Oh, can you edit the D? Ooh, I just see a question popping up from. Who was that asked that question?
Duncan asked, can you edit the DEMAS program prior to posting?
Absolutely. You can go in to the DEMAS code window here. You can modify it directly if you want to. So let's say I wanted to make this first go to 150. I could make it 150 like that. So the DEMAS code window that we have in front of us here is a full DEMAS editor. So it does have a compiler built into it. So if you fat finger a command or type something in wrong or something like that, it'll either fix it or warn you that it needs to be fixed. Some options in this V8 software have the ability to what I like to call modify them indirectly. So if I double click on the go-to, for example, I can change it here. And now I'm not messing with code because I know that can sometimes throw people off. If you're using the tree here, I believe we have the same capability here. We do not yet. So if you want to modify the DEMAS, it looks like you're going to have to go directly into the DEMAS. So, okay.
All right.
You're welcome, Duncan.
So you know where to find us on the web or call us direct. As Chris mentioned, thanks, Chris. Great informative hands-on webinar. This will be posted up to our website and YouTube channel. And we will be sending out notices for our part 2 series, which I think is going to be early November.
Yeah, we're going to try and do them every 30-ish days.
So thanks everyone for attending, and we'll see you soon.
Great. Thank you all very much. Have a great evening.